All right, so we're going to talk about the photoelectric effect. I zoomed way out so you can see we're in for it on this video. So settle down, open up page 69 and of the Red Book, Volume 5, and let's get to work, okay? Be patient, this is a long one. All right, and I'm going to go this way. All right. So we're talking about the photoelectric effect, page 69 of volume 5, the Red Book. There's a lot going on conceptually here, so a lot of this actually, even though this video is going to be long, the calculations are actually really easy. But for me, it's very difficult to do the calculations if I don't understand the concept. So, and this is a pretty darn important experiment historically. Einstein got the Nobel Prize for it, not for relativity. And so it's a big deal. All right, let's get into it. The short one-line version of this is high energy photons, or short wavelength, impact metal and emit electrons. I'll just grab a simple example of this. It's literally as simple as this. You shine, and maybe you can see this here. This is a piece of zinc. You can shine high energy, say shortwave ultraviolet light, and we'll do that in the next video. I'll show you this demonstration in real life in the next video. You just shine UV light on a piece of zinc, let's say, and it will emit electrons. That's the photoelectric effect. It doesn't seem like that much. All right. So, maybe I'll go to this board for, let me just go way over here and start over here. Oops, come on. Whoops, wrong way. This is why it was a big deal. A lot of people said light is a wave, and people had gone back and forth since Newton and Young and all these different people going back, Poisson. They were all fighting back and forth, is light a particle or a wave? And right around the turn of the century, every single experiment could be explained by the wave theory of light. And so the particle theory of light had fallen into disuse, so to speak, or was not considered as pure anymore. So this particular experiment, basically shining light on a piece of metal, had the following contradictions between wave theory and particle theory. So K here means kinetic energy of photoelectrons. So that's the electrons that are emitted. So the kinetic energy of the electrons emitted off that metal. The wave theory predicts if you have more intensity, you would have more kinetic energy, and we'll talk about this thing called stopping potential in a minute. Basically, you need a larger battery to stop the electron from moving, right? You can apply a voltage and stop it from moving. The particle prediction says you should have the same stopping potential regardless of intensity, meaning no matter how bright or dim the light is, you need the same size battery to stop the electrons from flowing. Okay? The dependence of the photoelectron production on frequency. Any frequency should produce a photoelectron as long as the light is bright enough. That's what wave theory predicts. Whereas the particle prediction said there should be a cutoff wavelength. And there's a couple more things here. You could pause this, you could read this, but that gives me back to what we're doing here. All right, and let me try to show a screen share right now so some of this makes sense. I'm going to show a simulation. All right, here's the idea. I'm going to turn up, and let's start here. Let's just start right here. We're using sodium. Let's use zinc. And our short wave is somewhere around 250, I think, or something. I'm going to turn the light up, so I'm going to turn up the intensity. We see that there are some electrons emitted. So these things moving here, I want you to think of each of those as a little minus charge moving to the right, okay? And let me clear out my drawings. All right, so here was the big deal. As I change the wavelength, as I make this shorter and shorter, we see that there are no longer photoelectrons being emitted, regardless of how much light intensity I use, right? And so if I actually crank this, I'm going to use a very low intensity now. And I'm going to go to a really short wavelength, somewhere in here. And we see, even at ultra low intensities, photoelectrons are emitted. This says we should treat the light as a particle. So it says light is particle. That was a big deal because, again, up to this point in history, every phenomena that you could think of could be, now it might be complicated, but you could model light as a wave, and you could do Snell's law that way, you could do geometric optics that way, polarization that way, all kinds of things. But this experiment only made sense if we think of light as a particle. It fundamentally changed our viewpoint. And polarization, we usually have to treat light as a wave. So we see this introduced this concept that in some experiments, light has to be treated as a wave, say diffraction, and in some experiments, light has to be treated as a particle. And I like thinking about polarization is the only one, is one that I think of as really you got to use light as a wave, and the photoelectric effect, we really have to treat light as a particle. All right, so let's get into this. Again, high energy photons, short wavelength, impact metal, and emit electrons. We see there's this one special wavelength, right? There's a cutoff wavelength. If the wavelength of your light source is greater than the cutoff, no photoelectrons. Now let's flip this backwards. You probably know that C equals F lambda here. If we rearrange this, right, we also see that, so for long wavelengths, we would get short, low frequencies, low energy. So basically, it's important to remember long lambda, low frequency, low energy. So low energy, low frequency, long wavelength, that's how I remember it, low, 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 will not emit photoelectrons. Okay, that's a huge deal, and that's probably the biggest deal out of this. Now, if you want, you could read the E. This is the energy of a photon, E subscript gamma, hc over lambda. Here's your constants. This is a really convenient number to remember, to 4 sig figs there. hc is 1240 eV nanometers. 1 eV is a tiny amount of joules. Just in case that's not showing up, that's 10 to the 19th joules. And the amount of kinetic energy for the emitted photoelectrons is given by the energy of the photon minus this work function. The work function is a property of the material, whether I use sodium or zinc or whatever. So sodium is something like 2.5 eV work function, meaning the photon needs at least 2.5 eV to emit a photoelectron. If you use a higher energy photon, it will emit and have lots of kinetic energy and it will become flying out really fast. Zinc is somewhere around 4.3 eV, so you need much higher frequency, much shorter wavelengths, much higher energies to emit electrons. And for the same photon energy, a photoelectron from zinc will be much slower than a photoelectron from sodium. Now, in case you're wondering, most of the time, pretty much every exam question I've ever written, and usually we don't need to worry about special relativity here. You'll see when we get into the problem. So fortunately, kinetic energy max, we don't have to think about the Lorentz factor gamma at all. It's just 1/2 mv squared, usually. And you can check that later by checking if this is close to 10% of the speed of light. All right, now, let's go over to board 2. All right. We're going to see some plots here, and I'll try and make these in the simulation in a second to kind of visualize this. These were some of the measurements they took. What they would do is they would apply a voltage and see how much current is measured. And actually, let's get to that right now. Let's get to the simulation right now. All right, so I'm going to pull up a chair. Just give me a second. All right. So I'm going to try and talk about current versus battery voltage. So I want you to notice right now, this is the voltage. It's right now at 0. So that's the battery voltage. Notice right now there's not much current. In order to make this work well, let's see. Let's ramp the intensity up to about 50%. Whoops. Okay, and just so I could see this, I'm paying attention to this plot right over here. All right. Now, in addition to watching that plot, I want you to be looking at this voltage. Notice there's some current now, and I want you to look carefully at what happens on these two plates right here and here when I start turning up the voltage. Okay, so that's a lot to watch. Okay, I'm going to turn up the voltage very slowly. Okay. Now, maybe you can see this, and I'm going to emphasize this. On this plate, when I turn up the voltage in this direction, right, this is the plus terminal of the battery. This is the minus terminal of the battery over here, so this is mine. So I get some charge building up on these plates, and they're trying to show that hidden inside of there. I don't know if you could see that on your screen, right? And notice, what is this going to do? When the photoelectron is ejected from the metal, okay, remember, when you think about one of these photoelectrons being ejected, it's going to be attracted to the plus plate and repelled by the minus plate. Opposite charges attract, like charges repel. And as a result, all of these photoelectrons are able to get to the collector. Now, this collector over here is sometimes called the anode. And this emitter over here is sometimes called the anode, if you're reading in the literature, okay? So you'll see different sources. I call it emitter and collector. I don't know why, but whoa. Did I write anode for both? Whoops, sorry. This is a cathode. My apologies. Right, so the plate that's collecting the electrons so that you can measure the current is called the anode. The one that's being impacted by the light is the emitter, and we're going to call that the cathode. Okay, now let's watch carefully what happens to the current when I reverse the battery voltage. Sometimes that's called reverse bias, and I'm getting way too many drawings on here, so let's see this. We're going to watch the current right here when I flip the battery voltage. I'm going to reverse the bias and watch the current number and watch the current plot. Here we go. Okay, now it's a negative voltage. Look at what's happening there. Do you see that? Now this plate is negatively charged. The collector or anode is negatively charged, whereas the cathode is positively charged. And notice the electrons are not able to reach the anode, and notice there's no more current. They're ejected and they come right back. They're ejected and they come right back. And if you watch, some of these get almost all the way there. Oh, look at this one. Look at this one. Oh, almost. They're not quite able to make it. And let me stop. Let me change the voltage down to negative 1 point. Whoops. Negative 1 point. Trying to get negative 1.2. Some of them will probably get very close, but don't quite make it. So approximately, we see that it takes about 1.2 volts in reverse bias or backwards to stop this. So we say that it takes a stopping potential of 1.2 volts. We do not include the minus sign on this by convention. So when you read the textbook, this is pretty confusing. We need a negative voltage to stop the electron flow but we call this, basically this is the magnitude of that voltage, right? It's a positive number. All right, so if we go back, I'm going to stop the share for a second, go back to the board, right? That's what this is talking about. And what we see is if you use a lot of light or a low intensity light, a bright light or a dim light, the stopping potential is the same for a given frequency, right? Assuming you're keeping the frequency fixed, which we were, right? And so that, right, you might get more electrons emitted, but we see that these electrons, no matter how many get emitted, are always going to get pulled back to the positive plate. Okay? So, and we see that the photons ejected with the maximum speed are the ones that just barely reach there. There's a bunch that come out here, right? And why would they possibly not be at max speed, you might ask? Well, just imagine if some of them bumped into some materials or were attracted slightly, or maybe they were shot off at an angle, whatever. So there's all kinds of reasons they may not come out of the metal at full speed, but assuming you have one that's right on the surface, pointed the right direction, and the photon hits it just right, and it comes out, it'll hit max speed. But a lot of them, maybe they'll bump into a few molecules on the way out and lose some speed. All right. So in this case, the kinetic energy max is equal to E, which is the magnitude of the charge on an electron. Oh, it's not joules, it's coulombs, fool. What am I doing? Coulombs. That C means coulombs. All right? And V, remember, this is the magnitude of the stopping. So this is a positive number, and this is a positive number. They're both magnitudes. It's the magnitude of the charge and the magnitude of the voltage. All right, all right. All right, so in this case, that's great. Oh. And the other thing that we can see, and I'll show you this in just a minute, we saw that there's a cutoff frequency, right? Below the cutoff frequency, this would be low energy. And this region would be high energy. In the low energy region, no matter how bright you make this, you don't need any stopping potential. And above this high energy, right, we see, or above this cutoff frequency in the high energy regime, we see that the stopping potential, right, increases as the energy goes up. All right? And that's basically given by, we saw earlier, let me just rewrite this equation over here. We saw that K max, and I'll get out of the way in a second, is equal to E gamma minus phi, this material work function, right? But so, and we just saw this, E Vs should equal Hc, let's use frequency, Hf minus phi. And notice, if I'm clever, you'll see this in a lot of lab reports in senior lab. If we divide everything by E here, right? Notice the stopping potential should look like, it should be linear, proportional to the frequency with slope H over E. And if this is given in, if the work function is listed in electron volts, phi over E is in volts. All right? And notice that intercept is negative down here. So that would be phi over E down there. All right. And let's take a look at the simulation, verify this actually happens here. Oh, it's a simulation, but yeah. Told you this is a long video. All right, so we see that no matter what intensity you use, right? If I sweep this out at high intensities, I get a large current. At low intensities, I get a low current. That matches the graphs we saw. Now let's look at, what was it? Current versus, oh wait, I wanted to get frequency involved, I think. Right, so in this case, this is the plot that we want. And let's go to zero stopping potential here. Oops, come on. Hard to get to zero. There, got this to zero. And so now what I'm going to do is I'm going to sweep the frequency. And let's start down here at low frequency, and let's turn this off and then back on. All right, so right now I'm at very long wavelength, very low frequency, and I want you to pay attention to this graph, right? So right now we see no energy because the frequency is so low, the energy is so low, the wavelength is so long, I can't emit photoelectrons. And as I go this way, this is still not emitting. And notice this issue that we're having here, right? This is not easy to see. Notice we're already getting into the ultraviolet part of the spectrum, and the wavelength is still too long. So, right, that's why I had to use, in the next video, you'll see I have to use a UV lamp. And long wave UV is not enough to emit photons. And then somewhere right around here, it should start kicking in. Maybe it's right here, about 288. And now we can see this. As I keep increasing the frequency, it looks linear. And that's supposed to be what we predicted according to our equations. And this is what Einstein got his Nobel Prize for. Maybe this is the time to go to the final board. Oops, wrong way. There was your two plots. What was the historical importance again? And this is the last thing before we wrap up. Up to this time, all optical phenomena could be explained with the wave theory of light. Photoelectric effect can only be explained by modeling light as a particle. All those predictions that I showed on the very first board at the very beginning of this video, they only make sense, right? Basically the particle model correctly predicted all the behaviors, and the wave theory incorrectly predicts all kinds of behaviors that are not observed. So that was a big deal. And so after this, we see that some experiments, such as a polarization experiments, you're going to have to model light as a wave. In other experiments, say the photoelectric effect, we have to model light as a particle. This basically forces us to accept particle-wave duality. Basically, if light is in an experiment where it's forced to act like a wave, we should model it as a wave. If light is in an experiment where it's forced to act as a particle, we should model it as a particle. And that's basically it. But that's a big deal. I'll show you a physical example in the next video.